White holes are curious mathematical opposites of black holes. And they were discovered mathematically in, I think it was the early 1970s, when black hole mathematics was maturing. You have the idea, how do you make it work? You go through the equations, bada bing, here's this black hole. It works. It's predicted by Einstein's relativity. He didn't predict it. Using his own theories and equations, he did not go there because it was too extreme even for Einstein to reach. We land there in the early 1970s, late 1960s. Here's a black hole, a region of space, nothing comes out ever. It's a collapsed region of space-time. And we have evidence for them in the centers of galaxies as endpoints of the death of stars. At the time, you realize you can take the equations that give you a black hole, and you realize, it turns out, there's another solution to those equations. It's not that complicated to imagine. If I take the number 9, and I ask you, what's the square root of 9? What would you tell me? You'd say 3. Because 3 times 3 is 9. So 3 squared is 9. Square root of 9 is 3. So we got that, okay? So the answer to the question, what is the square root of 9, is 3. However, I now ask you, what is -3 times -3? It's also 9. So in fact, the answer to the question, what is the square root of 9, has 2 solutions, 3 and -3. They're both legitimate solutions to that question. One is not more better than the other. The equations that give you a black hole, there's a second solution to it. It's the mathematical opposite of the black hole, where everything only ever comes out of it. What possible other word would we pick for this? A white hole. Early 70s, people said, all right, we got this. What would a white hole look like? Is there evidence for one in the universe? So we trained the telescopes on the universe. Found none. So right now, white holes are in the repository of science fiction ideas that you might want to do something with or not. But there's no evidence for them as being real objects in our known universe.